Okay, so we're now going to have a look at these definitions and explore how they apply to a familiar situation involving circular motion. So here we've got a top-down view of the Earth's orbit around the Sun. This distance there to the radius of the orbit, I'm just going to label R. It's given a special name in astrophysics, and it's called an astronomical unit, the distance between the Sun and the Earth. But for now, I'm just going to call it R. And we know in 365 and a quarter days, the Earth will go round that orbit once. And I've already said that the shape of that orbit is near enough a perfect circle. So I want you to imagine this Earth in orbit around the Sun. And I would just like you to imagine we started looking at it at this point, and just as with regular displacement, it's helpful to state a point where you've got a 0 point of angular displacement. So we can say here that theta equals 0. Now, we then take a snapshot as it's going round of the Earth a season later, so a quarter of the year later, when it would be there in its orbit. That distance hasn't changed to the circle. We're going to still call that distance R. And all the while, it's orbiting around. Now, in this case, when it's up here, we can define its angular displacement. So our angular displacement at that point is going to be simply this angle there, the angle to which it's moved through. So that's 90 degrees for that point in the orbit. Importantly, very rarely do we measure angular displacement in degrees. It is 99% of the time we use radians. And you have to double check based on the question, but very rarely does it come up. So in this case, we've got 90 degrees, which is pi by 4 radians. Is it pi by 4 radians? No, it's pi by 2 radians. So the angular displacement there is pi by 2 radians. And from that, we can see the definition. In a similar way, the definition of displacement is the change in distance in a certain direction. We can just have a definition of angular displacement as the angle an object has moved through. And when we introduce a definition of a quantity, we talk about what its units are. It's going to be measured in radians. Already, you can see the similarity between angular displacement, because instead of talking about a distance moved through, we're talking about an angle moved through. But we can also see that it's clearly not the same thing. So in this case, if we were to talk about the displacement of the Earth at that point, we'd actually be talking about this line there, going from there to that would be the displacement, which is absolutely not the same thing as the angle through which it's turned through. So you can see that those two quantities are related. They've got a similarity, but they're not the same thing. The displacement will be represented by a line joining the Earth at those 2 points. So we've then got angular displacement. If we then look at this new quantity here, angular velocity, what we have from our normal or regular quantities here compared to our circular quantities, we have a definition of velocity. The velocity is defined as the rate of change of displacement. And remember, in the formula, that's written as V equals delta S over delta T. If you love doing differentiation in maths, you'll be familiar with writing it as ds dt. But we've got here that velocity is change in displacement over the change in time. Now, that very closely links to the definition of angular velocity. And if regular velocity is the rate of change of displacement with time, then simply the angular velocity is going to be the rate of change of angular displacement, or to put in a bit of a short term, the rate of change of angle with time. Now, just as we've had the equation here for velocity, we can write an equation for angular velocity. Omega equals, it's going to be our change in angle, delta theta, divided by delta t. Really important equation, this. It is given on your formula sheet, but it's one of those equations where knowing it off the top of your head is really important for your understanding, and you're going to need to be applying it to problems very quickly. So it's something that you do need to remember. So delta theta divided by delta t, what are its units? Well, delta theta is measured in radians and time is measured in seconds. So we've got radians per second. So our units here of angular velocity are radians per second, often written like that. If we apply this to our example, we've got the Earth going from here to here. Well, we've already looked at what our change in angle or angular displacement is, and our change in angle is 90 degrees or pi by 2 radians. So for this example, e.g., we've got pi by 2 radians, and we're dividing that by the time. So we've said that it takes the Earth 365 and a quarter days to do the whole orbit. So we're dividing that by 4. So to do a quarter of the orbit, that is going to be divided by 91.3125. You then can put that into your calculator and you can get the angular velocity of the Earth. That gives you, I'm going to just give it to two significant figures, 0.017 radians per second. Part of your today we'll be practicing these questions. So these aren't the only examples we're going to look at. So we've got our definition of angular displacement. We've got our definition of angular velocity. The last thing that makes sense to look at is this quantity here, angular acceleration. Now, you can guess the definition of angular acceleration. We said that for acceleration, that is the rate of change of velocity. And it's given by the equation A equals delta V over delta T. Again, if you love differentiation, dV dt. The same thing follows for angular acceleration. It's going to be equal to delta omega over delta T. At this point, I've got some good news. We do not need to worry about angular acceleration. In fact, this whole quantity is not on our specification. So we don't need to know the definition of it, and we're going to look at why in the next video. So just to recap, through this example, looking at a top-down view of the Earth orbit, we've seen that the angular displacement can be defined as the angle through which the object in circular motion is turning through. And we can see that the angular velocity is the rate of change of angular displacement in the same way that regular velocity is just the rate of change of displacement, where the regular velocity is given by the displacement divided by time. Angular velocity is given by the change in angle divided by time. They're not the same thing, they're just closely related. So in the next video, we'll hopefully look at why we can forget about this idea of angular acceleration for what the problems that we are looking at.